Hi, good day. So let's have another example for the design and analysis of flexural members for a steel design. So determine the design flexural strength LRFD and allowable flexural strength ASD for a W18 by 97 with Fy equal to 345 megapascals and an unbraced length of 11.6 meters. Assume C sub B is equal to 1.0. So from our database, so these are the properties of W18 by 97. So first thing to do is we are to check the compactness of W18 by 97. Again, so if we are using an I-shaped section or wide flange, so we are considering case 1 and case 9. So flexure in flanges and flexure in the web. So from our previous video, for the flange, what is the equivalent of the width to thickness ratio? We have that as the B over T, or to be more specific, that is the width of the flange divided by twice the thickness of the flange. And this is now equal to, the width of the flange is 282 millimeters, then divided by twice. The thickness of the flange is 22.1, and this is equal to, we have that as 282 divided by twice of 22.1. So we have that as 6.38. Then for the web, the width to thickness ratio is the H divided by the thickness of the web, or simply equal to the total depth of the beam minus twice the value of K, then divided by the thickness of the web. So we have, what is the total depth of the beam? We have 472 minus twice the value of K is 32.3, then to be divided by thickness of the web, we have that as 13.6. So we have, this is 472 minus twice of 32.3. Then divided by thickness of the web, we have 13.6. So we have that as 29.96. We have 29.96. So these are the slenderness ratio. So slenderness ratio for flange and slenderness ratio for the web. So we need to compare these values to our lambda sub p. So what is the equivalent of lambda sub p? For the flanges, we have 0.38 of the square root of E divided by Fy. So we have to compute for that value. So this is 0.38 of the square root of E divided by Fy. So this is now equal to 0.38. Then the square root of 200,000 megapascals divided by the Fy of our section is 345 megapascals. So let's have this value. We have that as 0.38, then the square root of 200,000 divided by 345 megapascals. So we have that as 9.15. And then, for the value of the y sub p for the web, that is 3.76 of the square root of E times Fy. This is 3.76 of the square root of E divided by the value of Fy. And this is now equal to, we have 3.76, then multiplied by the square root of 200,000, then divided by 345 megapascals. So we're just to edit this input. So replacing 0.38 with 3.76. And that is equal to 90.53. So as you can see, we have here the values of the lambda sub p are greater than the width to thickness ratio for the flange and the width to thickness ratio for the web. So therefore, we can conclude that both flange and web are compact. So if we have compact flange and compact web, then therefore we can use section 506.2 of our NSCP 2015. Now we need to determine which zone this one will fall. So is it zone 1, zone 2, or zone 3? So based on its given unbrace length. So according to this example, our unbrace length so our unbrace length is equal to, you have that as 11.6 meters. This is a quite long beam. So the unbrace length is equal to 11.6 meters. So we are to compare first its value to the value of L sub P. Okay, L sub P, which is equal to 1.76 of Ry times the square root of the modulus of elasticity divided by the Fy. Okay, so let us compute the value of the L sub P equal to 1.76. The radius of gyration with respect to the y-axis, then multiplied by the modulus of elasticity divided by the value of Fy. So we have this as 1.76. Okay, the value of our Ry is equal to, that is, we have 67.3, then multiplied by the square root of 200,000, divided by 345 megapascals. So this is L sub P in terms of millimeters. Okay, we have that as 1.76. Our Ry is 67.3. Then the square root of 200,000 divided by 345. So this is 2,851.89. 2,851.89 millimeters. So compare that to our unbrace length. This is the same as 11,600 millimeters. So which is, okay, our L sub P is way less than our L sub B, which is equal to 11,600 mm. Okay, so therefore, next step. So we need to check if maybe this section is under zone 2. So for us to determine the value of, or for us to determine if it is under zone 2, I will be needing this equation, and we are to compute for the value of L sub R. Okay, and also we'll be needing the value of the R sub TS. Okay, so since again, the value of our L sub P is less than the unbrace length, so we need to compute for the value of the L sub R, and our equation will be this one. Okay, so we'll be reading this equation. But first, again, we are to compute for the value of the R sub TS squared, which is equal to the square root of the moment of inertia with respect to the y-axis, the warping constant divided by the section modulus with respect to x-axis. So this is now equal to, we have the square root of, so what is IY for W18 by 97? Okay, we have that as 83.7. So we have 83.7 times 10 raised to 6. Then multiplied by the warping constant, we have that as 4,240. Then times 10 raised to 9. Okay, then to be divided by the section modulus with respect to the x-axis is 3,080. Okay, this is times 10 raised to 3. So we'll be having the equivalent of the R sub TS squared. This is now equal to So this will be in terms of the square millimeters. So we have the square root of 83.7. This is times 10 raised to 6. Then multiplied by warping constant for 240 times 10 raised to 9. Okay, then divided by 3080 times 10 raised to 3. So this is again in terms of the square millimeters. But if we are to take the square root of both sides of our equation, we'll be having the equivalent of the R sub TS. So from our calculator, all we have to do is take the square root of that value. That is 78.21. So the value of the R sub TS is 78.21 millimeters. And then next we have for the value of C. Again, so from our reference, so the value of C can be equal to 1.0 for doubly symmetric I shape. So that includes our section at the W18 by 97. And then, so what else? We need the value of the H sub O. So from our previous discussion, how do we compute for the value of the H sub O? So we have H sub O is equal to the total depth minus the thickness of the flange. So we have the value of the H sub O is now equal to, what is the depth of this section again? That is equal to 472, then minus 472 minus the thickness of the flange, that is 22.1. So we have 472 minus 22.1. We'll be having the value of the H sub O is now equal to, we have 472 minus 22.1 is 449.9 millimeters. So I think we are now ready to substitute all values to our equation. So let us now compute for the value of the L sub R. So L sub R is equal to 1.95 of RS, or R sub TS. This is 78.21. Then multiplied by the modulus of elasticity. So we have that as 200,000 megapascals. Divided by 0.7, our Fy is 345 megapascals. Then multiplied by the square root of J. What is our J? It's 2,440 times 10 raised to 3. So this is 2,440 times 10 raised to 3. Then, to be multiplied by our C. So again, the value of C is equal to 1.0 for symmetrical I-shaped sections. Multiplied by 1.0, then divided by, what is the value of our S sub X? Is 3080. We have that as 3080 times 10 raised to 3. Then multiplied by H sub O. Our H sub O is equal to 449.9. Then we are to multiply this value again to the square root of. This is 1 plus the square root of 1 plus we have 6.76. Then multiplied by the values. So we have that as 0.7. 0.7 of Fy, that is 345 megapascals. Our S sub X is equal to 3080 times 10 raised to 3. Then multiplied by H sub O, we have that as 449.9. Then to be divided by the modulus of elasticity, this is 200,000 megapascals. The value of J is 2,440 times 10 raised to 3. Then multiplied by the value of C, again, that is 1.0. Then this quantity squared. Okay? So this is our equation, okay, and the values, okay, for the value of L sub r. Okay na, so we are ready to compute for the value of the L sub r. And this is equal to, so again, I'll be starting on this term. So we have that as 0.7 of 345, then 3080, okay, times 10 raised to 3, and then multiplied by 449.9, okay, to be divided by 200,000, okay, times 2,440. Then we are to square that value, and then multiplied by 6.76. Okay, then plus 1, then square root again, then 1 plus that value, then square root again. Okay, then to be multiplied by the square root of, or that will be answer multiplied by the square root of 2,440 times 10 raised to 3, then divided by 3,080. So we are missing with 1 0 on the numerator. Okay, we have 3,080, okay, times 10 raised to 3, then multiplied by 8 sub o, that is 449.9. And then to be multiplied by, we have that as 200,000, then divided by 0.7 of 345 megapascals. And then multiplied by 78.21 times 1.95. And that is equal to 9,247.20. We have that as 9,000. Okay, so this is 9,247.20 millimeters. So if you are to recall again the value of our LR, LB, and LP, okay, so we can now summarize. Okay, so we have the value of our L sub P is equal to 2,851.89 millimeters. Then the value of our LR is equal to 9,247.20 millimeters. And the value of our L sub B, the unbraced length, is equal to 11,600 millimeters. So therefore, L sub P is obviously less than L sub R, and L sub R is less than L sub B. So if we are to recall our reference, so we have here the L sub B is greater than the L sub R. So that will be the design of beams under zone 3 with elastic buckling. So this will be under zone 3. So we can compute for the nominal moment, okay, using this equation. Okay, so we are now ready to compute for the F sub CR. Okay, for the value of the F sub CR, okay, so we have that as the F sub CR is equal to, again, the value of our C sub B is equal to 1.0 multiplied by pi squared, then 200,000 megapascals for the value of E. Okay, then divided by the unbraced length is 11,600 millimeters. Our R sub TS a while ago, I think is 70. It is the 78.21 millimeters. So this is divided by 78.21 mm, so quantity squared. And then to be multiplied by the square root, this is the square root of 1 plus 0.078, then to be multiplied by the quantity, it's the value of J. We have that as the 2,440, this is times 10 raised to 3. Then the value of c is simply 1. Then divided by s of x is 3080. This is times 10 raised to 3. Then multiplied by our h sub o. Our h sub o is equal to 449.9. Okay, then multiplied by 449.9. Okay, then this value again to be multiplied by the L sub b, 11,600, okay, divided by R sub ts, the 78.21. Then quantity squared. Okay, so computing for the value of the F sub CR. Okay, so since that is 200 megapascals, the value of this F sub CR should be in the mega pascals. So we have that as, let's say, sheep pi squared, then multiplied by 200,000 megapascals. Then to be divided by unbraced length, 11,600, divided by RTS, that is 78.21. This quantity squared. Then answer multiplied by the square root of 1 plus, we have 0.078. Then multiplied by 244t times 10 raised to 3, multiplied by 1. Then divided by 3080 times 10 raised to 3. Then multiplied by h sub o, we have that as 449.9. Then to be multiplied by again by the unbraced length, 11,600, divided by the 78.21 squared. So we have that as 179.94. 179.94 mega pascals. So how do we compute for the nominal moment? That is m sub n equal to f sub cr times s sub x. And it should be less than or equal to the m sub p. Again, we have m sub n is equal to the f sub cr multiplied by the s sub x. Okay, but it should be less than or equal to the value of the m sub p. So let us now compute for the m sub n. Okay, we have m sub n is equal to f sub cr. We have 179.94. Obviously, this is in newtons per square mm. And s sub x for this section is 3080 times 10 raised to 3. So multiplied by 3080 times 10 raised to 3. This is millimeters raised to 3. So to be divided by, or if we are to multiply, 1 kilonewton is to 1000 newtons, and multiplied by 1 meter is to 1000 millimeters. Okay, for our final value to be in kilonewton meter. So we'll be having the equivalent of the nominal moment capacity, that is equal to we have 179.94 times 3080 times 10 raised to 3. Then to be divided by 1000 squared. So we have that as 554.22. 554.22 kilonewton meter. But this should be less than or equal to our m sub p. So what is the equivalent of m sub p? M sub p is equal to the Fy multiplied by the C sub x. So we have the value of m sub p is equal to, our Fy is 345 megapascals. Okay, then the value of the C sub x is equal to, that is 3,460 times 10 raised to 3. Yes, 3,460. Okay, 3,460 times 10 raised to 3. Then, okay, to be divided by 1,000 squared, okay, for the value of m sub p, ay to be in kilonewton meter. So let's have that value as 345 multiplied by the plastic section modulus 3460 times 10 raised to 3. And to be divided by 1,000 squared to be in kilonewton meter. And we have that as 1,193.7 kilonewton meter. So let's check this conversion. 1,193.7 kilonewton meter. Obviously, okay, so that we have our nominal moment capacity m sub n equal to 554.22 kilonewton meter is less than the m sub p. So this is okay. So we are now ready for the ultimate or that is the design flexural strength. Okay, for the LRFD. So we have our mu. Okay, the value of mu is equal to p multiplied by the m sub n. And this is equal to 0.90 of 554.22. And this is now equal to 554.22 multiplied by 0.9. So 498.8. Let's say this is 498.80 kilonewton meter. So this will be our answer for the design flexural strength under LRFD. Okay, then for the ASD, so our allowable, the allowable flexural the allowable flexural strength, that is the we have the nominal moment m sub n divided by the factor of safety. So this is equal to 554.22 divided by 1.67, and this is now equal to 554.22 then divided by 1.67. That is 331.87. So this is 331.87 kilonewton meter. So this will be our answer for the allowable flexural strength. So that is under ASD. So this will be our solution for this example.